Cheers.
Hey,
So,
hey
by the way,
there.
who's the official host of this, Eduardo?
We are co-hosts, right?
Yeah, yeah. Well, welcome everybody from my side. We have a special stream, a joint stream. So we're both on my channel and Eduardo's here, and we're gonna learn about astrophysics today. We're gonna learn about the
Um,
unusual universe, and we don't have an agenda. We're gonna see where the conversation leads. So there's my introduction.
okay, that's your introduction. I would say that the interesting thing about tonight would be more to see, like, I mean, that's a pretext. Like, the unusual universe is just a pretext to talk about more about the philosophy of science, and because I think sort of cosmology and astronomy in general, they are one of a kinds of science, in the sense that you cannot really reproduce the objects you're studying,
Yeah.
and so there's no such thing as reproducibility, which is one of the tenets of science in general. You should be able to reproduce the objects that you are studying, or like the studies that you do. And usually what what happens in cosmology, especially cosmology is like the science of the whole universe, is that we happen to have just one universe
That's
to
it. That's all
study.
we have to work
That's
with.
it. We have to. That's what we deal with. So we have two choices. We either reject this on philosophical grounds, like we reject like the how would you say, like the scientificness, the scientific content of cosmology.
Right.
We can reject it on philosophical grounds, based on the fact that it's not reproducible.
It doesn't meet a certain criteria. Sure.
Yeah, sure. So I mean, that's one of the things that it would be nice to discuss, is in discussing science, right? Because when people talk about science, there are certain criteria that you usually think they are sort of necessary conditions
Right.
in order for something to be scientific. And well, it turns out, if you're really strict about this, then I wouldn't say cosmology is science in the same way you define, for example, particle physics or biology,
Chemistry.
chemistry. So that's again, it's debatable. I
Yeah,
don't know
yeah,
what's your take on
that,
this.
and that's something that can't be settled within science, right? That is a philosophical question, and it's something that's been wrestled with for a long time. Of like, what do we even count as science? Now, I'm with you. I think we're in agreement that like what you do is definitely science, even if it doesn't meet if it doesn't meet the criteria of reproducibility. And if we're not going to have that, we're going to have an issue with many different, well, really all the forensic sciences, right?
Yeah.
Where we're
History.
just trying to understand the history of anything, right? And that's going to have evolutionary sciences, your branch, and I want to learn more about what you've studied specifically too, because we haven't had a chance to talk about it much more. And I don't think most people are going to want to just kind of saw all that off. You know what I mean? I think most people are going to want to say, no, that should definitely be considered. Like there's boundaries. We talk about what those boundaries are, and there's probably some things that are called science today that I don't know if they would meet all the criteria that I think should be met. But even then, it wouldn't mean that they're not useful, right?
No, exactly. It's two different things. I mean, of course, you can learn. I mean, mankind learned a lot of stuff without knowing the scientific method for hundreds of years, for I would dare to say for tens of thousands of years. So it's not that it's not useful. So you can still learn stuff even without being scientific. Of course, it's a different thing. You have to be aware of the limits of what you're doing, but. If we, I don't know, at least as a physicist, I would say that the scientific method was born with Galileo. So if you cannot just then throw out of the window everything that happened before that, just because people were not aware of the scientific method. So the testing, and the whole process that is there when you have a scientific theory. So the testing thing, the reproducibility thing, the experiments, the way you set up the experiments in order to like to test or falsify a theory, and so on and so forth. But that was not explicitly stated, so to say.
Right. Yeah, it's interesting. Like the history of science is interesting there because you have, of course, major figures. Then you have Bacon, and you have the kind of classic four idols of the different idols that we try to eliminate to get very objective in our analysis. The way I think about it, Eduardo, and I'd be curious your thoughts on
Yeah.
this, is like it seems like at least a general agreement in philosophy of science is like whatever else science is, it has this sort of arch, right? Where on the left side of the arch we have our kind of empirical data that we've assembled, usually painstakingly, and we're using that to kind of work our way up inductively to some type of general theory, right? And then from there we have the kind of right side of the arch where we kind of come down deductively in our testing of the hypothesis and the theory and making predictions and seeing how accurate it is and stuff like that. And it seems like a lot, at least of the philosophers of science that I've read, are in agreement in at least that much, that like whatever else the scientific method is, it's going to look something like that. But then there's like massive disagreement on things like, does something need to be falsifiable, like verificationism, falsifiability, stuff like that, or could we just use inference to the best explanation, for example, right? I know we talked about the multiverse before, which is kind of interesting, right? Because some people are like, well, first off, it just seems wildly extravagant, right? And somewhat ad hoc, but it also doesn't seem to be meet a criteria of falsifiability. But then people will push back and say, well, do we have to do that, right? It just seems like we could make an abductive inference here and just put it on the table of explanatory options. So, there's just a lot of debate, in all that stuff.
There's one thing that is that people usually don't think much about that, which is the fact that something is possible doesn't mean it's likely. It's like, because there's a lot of things that are possible. For example, the multiverse in principle is possible within the framework of general relativity and quantum physics, which are, to the best of my knowledge, they're the best theories we have. Like, as far as they've been tested on a wide range of scale, and so they are very good theories from that point of view. They are very reliable theories, and so this is sort of in agreement with both, and so it means it's possible. Well, in a way, it's possible, but then how do you decide whether something possible is then likely to happen, or is it realistic? That's a different thing. And people, there's this thing that most of the times when you debate about science, then people would come up with some kind of counterexample in order to sort of try to falsify your theory. This is like in any field. And so you could come up with this counterexample, which is possible within the framework, but still it's not likely. So does it make sense to debate theory based on this kind of philosophy? Like, in general, it's like I think we should always keep in mind that some things are likely, but again, they are possible but not likely. And so when we are debating different theories, competing theories for any field of science, then we should also keep in mind then the way you can assign weights, so to say, to different theories and like trying to estimate what's the likelihood of each theory to be true, then it's sort of subjective, or there must be some other kind of evidence. It's not so straightforward. There's always some debate around that. So as you said, the multiverse, like I would say, is a matter of taste, or I don't know, by Occam's razor, or by any other kind of not strictly scientific or not strictly mathematical tool. I would say it's not something I would endorse.
Yeah, no, I don't. I think it comes with a host of mostly philosophical problems, right?
Though I must tell you something. So there's many versions of that theory. I mean, when you talk about multiverse,
right,
you can be talking about one theory, which is the that theory that says that is based on quantum physics. As you know, that you have this superposition of states. I don't know if you know the principle, but just to recap on this. Particles of matter. Can you hear me?
So yeah, no, sorry, you just froze up there a bit. So just rewind like 15 seconds.
Yeah, sorry. So there are two kind of multiverse theories, as far as I know. So there's, which you would call multiverse. I don't know if it's the technical term for both of them, to be honest. But the first one is the one that says that the universe is splitting basically every second, even less than that, of course, because it's based on the principle that in quantum physics you have different states that exist at the same time. So a particle is, until you go and measure it, it's a superposition of state. It's like the Schrodinger's cat thing, right? Until you don't measure that, the cat is dead and alive at the same time.
Right.
And so the electron has two different properties at the same time. Then you go and you measure and you find one, right? So it's spin up or spin down, or has some kind of velocity or momentum. But it's like, again, taking the cat, which is, I think, is easier object we can work with. It's in quantum physics, it's basically impossible. It's basically possible for particles until you don't measure it, until you don't actually measure that, to be dead and alive at the same time. And so what the multiverse, this version of the multiverse theory says is that actually there is a universe. So the universe is splitting. There is a universe where the cat is dead, and there is another universe where the cat is alive. And this happens all the time. There's like a multiplication of universes. So like there's, you can always trace in a deterministic way the history of the cat being, always alive, and then at some point it dies in this universe, or in this other one. It's like branching.
Yeah. Right? All possibilities are actualized.
Exactly. The other version is that there's many bubbles. So the thing is that, of course, we can make statements about the universe as we see it. I mean, the observable universe.
Yeah.
And the idea is that there's nothing preventing, the world, the universe, the cosmos, the everything from being composed of several sub structures. So like a small universe with different laws.
Yes.
Like you have different bubbles, and in each one of these bubbles you have different laws of physics, for example.
Right.
Or you might have different constants. You might have the same laws but with different fundamental constants. And the thing is that they explode, and they have this big bang, and whatever happens, because again, if the laws are different, then they might have different histories. Like some of them might collapse on themselves like after 2 seconds. Some of them might just go and undergo like this expansion, as we believe that's what's happening in our case. And so that's another version. But this second version is actually interesting because there are ways you might measure. Not really measure, but you can think about observations that might show you the fact that there are other universes like this.
Yeah, my the physicist I've had on a couple of times, Steve Barr, he's skeptical of the different multiverse, and you're right, because there's different models of it out there, right? He's skeptical, but he says the one that at least intrigues him the most, that might be worth looking into, is the one that you've just described, which is kind of like, these bubble universes. There's other models where there's sort of this proposed universe generating mechanism, right? And that pops out and it is interesting to ask, like why are these things being posited? And it's because there's certain things that they think that the multiverse would be able to explain, right? And I like what you said before about the idea of that just because something is possible doesn't mean that it's plausible or that it happened. I mean, even if we take another forensic science, just general history, and we look at the Great Pyramids, right? Like it's possible that they're there because of aliens, right? It's also possible that they're there because of a series of sandstorms, right? That's in the realm of logical possibility, right?
Exactly.
But
there's no physical law preventing that from happening.
There's no physical law preventing that. So then it's like, well, what considerations do we need here, right? Especially if we don't have certain criteria that would allow us to sort of run a series of experiments. Well, okay, if we're going to have multiple competing hypotheses, we can at least ask things like, what is its explanatory scope? What is its explanatory power? How contrived is it? How ad hoc is it? Do we have any other types of causes that produce similar effects today that we might be able to extrapolate back then, like people building pyramids today, right? So there's these like other like if we're going to allow that type of reasoning in science, which I actually am not. I think that the sort of inference to the best explanation certainly has a place. Certainly has a place in. I mean, we do it all the time, right? In our general reasoning. And it's a debate within philosophy of science if that should be allowed or if we should stick with like a strict falsification criteria or something like that. That's all very interesting. But if we're going to allow something like that, then we're going to need other criteria to help evaluate the hypotheses, right? Mm-hmm.
But even with this, of course, these theories, you do have some kind of falsification, right? You can find some, again, if with some of those, like as far as I know, string theory, it's very hard to find some way of falsifying them, and even let alone like testing them. But with the multiverse, for example, you could argue that if you have these different universes, and some of them might be expanding, then you should sort of see the collision at some point.
Well, yeah, they should smash into each other, right? Yeah, huh.
And that was something that was found. Actually, I remember a few years ago they found within the cosmic microwave background signal. So basically the lights, from the Big Bang, what they call it. It's like this microwave radiation that is coming from back then, from 13 billion years ago. And they found that, if you map it on the sky, then they found sort of a hole within it. Like it's very homogeneous and isotropic, except they found this place where it was darker than it should have been, that people would have expected. And then they were arguing that this hole in this radiation was due to the fact that there were two universes colliding. There was another universe sort of colliding with us. But again, it's like there was wild speculation in my opinion. But at least you can make up something that goes in the direction of, okay, there is at least something we can look at. And
yeah, there's at least something. Right?
There is at least something.
Yeah, that might be. And what that is it's sort of it's another kind of like intuitive thing, but it's based on degree of expectation, right? Like if this hypothesis is true, like what would I expect to see? And then do I see it? So the move there, I'm with you. That sounds like pretty wild speculation to me, but okay, we can entertain it. If I expect these sort of collisions, might we find some things that would leave, I guess, a residue of that or something, right? And I guess that's kind of what they're trying to claim that data point is, right?
Yeah.
But then other people go and they refine the multiverse models, because they're like, actually, we can't have these collisions. This would be too catastrophic, right? So then they have to kind of like tune up the models.
Yeah, sure. No, that's we have this tuning also in the standard cosmological model, so to say. It's like the cosmological theory that is like the consensus model, so to say, the consensus cosmology, which is again, it's we know that science is not democratic and blah blah blah, but whatever. It's like at some point we need to make a choice, and if we want to study the universe, we need to do it through some kind of lens, right? We have to, when you analyze the data, or even just thinking about the experiments, you need to have some kind of theory in mind, because you cannot just say, okay, let's just point the telescope at the sky and see what happens. No, you need to have something in mind. And so in this case, I would say that the theory is interesting, because it's even though it might not be true, at least it's giving us hints of what you can take, like where to point the telescopes at, for example. What kind of signals you should look for, what kind of evidence you need, for example, for, again, to confirm or kind of falsify the theory, especially with with some kind of, there's many classes of predictions that come with the theory, right? On different scales, because again, it's a theory. The cosmological model it's a theory of everything. So you can look at literally at everything, right? So you can look at galaxies, you can look at structures like galaxy clusters, so thousands of galaxies all together, and you can look at filamentary structures that are these gaseous structures that you find in the universe. You have these huge conglomerates of galaxies, so galaxy clusters, and they are joined there by these filaments, they are called. And so you find some kind of structures there as well. For example, the Milky Way happens to live on one of these filaments. So the interesting thing about this is that your cosmological model is telling you exactly, once you have a model, you can work out the predictions, and you can do some calculations. And this is telling you, for example, how many galaxies of this kind should we see in this kind of environment? What's their density? What's their mass? You can make a lot of predictions. And again, this is like something from a theory of everything. It's like from the whole universe, from the Big Bang to today. And then you can work out predictions on different scales. And again, this is one of the reasons why I think cosmology is, directly, it's not really testable theory. in classical sense that it's reproducible, or you can make real predictions. I mean, you can make predictions in real-time cosmology. It's sort of a new field. Like I remember 10 years ago they were starting to make, but it's more, it's when you talk about timescales in cosmology, you're talking about millions of years.
Right.
It turns out it might be hard to test.
There's a little bit of a waiting game there. Yeah.
Yeah.
So, Edoardo, tell us a little bit more about your specific area of research.
Cosmology.
Yeah, but like within that, like what are the specific questions that and for people who are on my channel and unfamiliar, actually just take us back. Where did you do your PhD, and then what did your postdoc work look like?
So I did my PhD in Madrid. Oh, it's freezing.
You're still here at my end.
Yeah, sorry, it freezes. Wait, let me just shut down a couple of things because I'll just leave this. So I did my PhD in Madrid, and then there I stayed for 4 years, and I was working on theoretical cosmology, and I was working on alternative models of the universe. And again, it's like I was working on alternative theories of the universe and trying to find out observables, mostly like physical properties that you could measure in actual galaxies, for example, or in galaxy clusters, or again, distribution of gas within the universe,
right.
The abundance of galaxies within the universe, that could tell you which one was the likeliest theory. So if, as I said, we have this kind of standard cosmological model, and then it's called, so this model is called lambda CDM. It's called lambda cold dark matter, so it's related to the fact that there are some ingredients within this universe. And I was investigating some kind of alternative theories where just to keep it simple, I was assuming some different properties for the unknown part of the universe. So there's basically 90% of the universe is unknown, in the sense that we don't really understand where this energy and this matter comes from, and of what is it in practical terms. We don't really understand it. And so there are different hypotheses. And so I was testing different models of this kind of the so-called dark sector, so the unknown part of the universe. If it works in one way, then we would expect, of course, to have some reflections on the observable properties. I mean, what we observe in the universe, at the end of the day, it's like stars and galaxies are luminous objects. But there's plenty of things we don't see because they are dark, right? There's not everybody in the not every kind of object in the universe emits light. Not everything is luminous. There's lots of dark objects, right? And so we only see the luminous ones. And so we have to infer the properties of the dark part by looking at the luminous part.
Right.
Okay. And so the thing is that you can model the dark part of the universe in several ways, with several different theories, so to say, and different approaches. And I was testing them. So I was working, for example, on the kind of predictions that these models had for large galaxies, so large galaxy clusters in the very early universe. So I don't know if everything is clear.
No, I love this. I love hearing this. Laura says he's unraveling the universe, and that is all we need to know. Well, somebody's got to do it, right? Somebody's got to take up that task. Yeah. So that's cool. And I mean, no, add whatever else you want to that. I mean, to me, all that stuff is really fascinating.
Okay. Is it?
Yeah. No, it really is, right? And I love the, I do love to think about, because to me, what you're doing is science, like it is, right? You certainly have other criteria that I think a lot of people who thought about whatever else a scientific method is about, it should have some aspects of mathematical modeling, right? Which which is interesting because like that's been like so forced into other sciences where it doesn't like it clearly doesn't work very well, right? Right. But the reason that's been yeah, but the reason that's been forced is because like people know that like the mathematization is like a hallmark of science, right? So like if I can formalize this somehow, then I will be a scientist, right?
It's being quantitative, right? You want to have
Right.
numbers, and if you can put a number somewhere, then it's like and some kind of graph, some plot, some image, then it looks like it gives credibility to your work, right? No matter what's the actual content behind it, because everyone can just write an equation and just say, "Oh, this is my modeling of the phenomenon." Yes, but
Yeah, and
does nature
we've
know
heard a
about your
lot about
modeling?
models lately,
Yeah.
haven't we, Eduardo? There's been a lot of models out there.
I don't know what you're talking about. But
You know, like so, like my undergrad is economics, right? So like I know all about the models, right?
Yeah.
And some of those models haven't worked out so great, right? They haven't.
no.
So it just gets messy. Like I think what people like about physics is a lot about physics is kind of like it's cleaner with the math, right?
Ah, yeah, sure. But because it's simpler to do with particles. Particles don't have intentions as far as we know. This electron is not going to say, no, I'm not going to do that.
Right. Yeah. Yeah. So like we would expect to be able to have more precision there, right?
Yeah.
And like and that's that to me I think is an important realization, right? That it shouldn't surprise us that when we're in physics that we're going to have more precision given the nature of the subject matter that we're studying than in economics, for example.
Sure.
Right. That just shouldn't be surprising, and we shouldn't. Certainly, I don't think all economists are like this. Far from it. But right, there is a tendency to think among certain economists like we can get the type of precision and control in economics that we have in physics. Now, I think that's a fantasy, right? Absolutely.
I think it is. But so one thing I appreciate about mathematics in economics, but in general, like mathematics in general is sort of the way that it's connecting variables. And so it's telling you how, if you have a theory and you have some variables and you have some some quantitative aspects to that, and you want to see how the interaction between these variables produces an output. It's like it makes sort of the logical statement behind it in a way clearer. It doesn't mean that the quantitative prediction is true, far from it. But it's more about the logic. I think that's something I try to do like myself when I think about any field. Like I try to sort of make some kind of mathematical model from it, not to quantify or make exact predictions.
Right.
It's more to understand what's the consequence. So if I have this interaction between these variables, then what do I expect the output? What's the trend of the output? Just if I raise this variable, if I increase this, is the output gonna decrease or increase?
Right.
To have this kind of general picture. But then, like I think, as you mentioned in economics, then economics again, it's a huge field. So it's I think it pretty much depends on the kind of subfield you're talking about.
Yeah, what branch of economics are we talking about?
Exactly.
Yeah, and I think so. Like most of the education I got was just your standard Keynesian economics, right? But then I was always very interested. Yeah, I was very interested in alternative schools too, like Austrian. But I'm not an Austrian economist because I don't think that you can just do like really good economic work just from the philosophical armchair.
Oh no,
right?
no. I agree
Not at all. So I think there's good insights from the Austrians.
Yes.
But I'm not an Austrian, so I think we're actually like in substantial agreement about there. Like I think a lot of what the other schools of economics have to offer, whether it's the Keynesian or Chicago school, whatever, there's good stuff there, even if I don't go all the way with all of it.
But I mean, it's like physics, or I mean, like any. This is something again. If we're talking about economics, I really don't understand the fact that you have schools, and then if you work within this framework, then you cannot really accept some some hints or insights that come from another framework. It's like the world is a complex place. You need more. I mean, maybe even if they are in contradiction, but still, like I think human nature is contradictory at times. So you cannot just assume one thing or the other. Like human beings are. They have some kind of superposition of different attributes
Right.
at the same time. So you cannot just take one set of like axioms, so to say, and then work out the consequences of that. Maybe there's also some kind of contradictory axioms might give some insights as well, because I think that there's a lot of how do you say, like, wiggle room in the way societies are shaped and human beings are shaped. But
Right.
that's not the case in physics. It's not like electrons can choose whether to be protons or to behave like something else.
Yeah.
I think that's
Yeah, I haven't read
intentionality.
I haven't read the Austrians lately, but I mean they have like good insights, right? That humans, and it's a lot of it's Aristotelian, right? That humans act for an end, right? And that
Yeah, sure.
and stuff like that. But again, I don't think you're going to be able to deduce from the armchair how they will act all the time from the armchair when you want to put in a minimum wage, for example, right?
Yeah.
I think for that we need to actually go out and take a look, right? And so that's kind of like the mistake I would make of like the purely almost sort of rationalist. So yeah, here's maybe a good way to frame it. Like, it seems like the extreme of Austrianism is like a purely rationalist deductivist will do all science from the armchair. Not going to work. But the other extreme of economics like ignores any of the sort of just human nature elements. Right? You see what I'm saying? And like it's just all we will be able to get this down to kind of physics and create any environment we want, right? At some point. And that seems to me in excess to like whatever else we want to say about how much of a minimum wage we can or should implement or how much we get away. Like it's obviously going to have a certain perverse incentive. Like the Austrians are right about that, right? Like they're definitely right in a general sense, right? They get that like kind of just from the armchair, and it's not wrong. But to figure out how it's going to work or how it's going to play out, that's where we need to take a look, right? Mm-hmm.
Yeah, I see your point. I mean, I agree with that. But it's like in general, it's like I would make a parallel with physics, like Einstein did. Like he had this general theory of relativity. It started from two very clever ideas, like axioms, I would say, like the principles. And then he worked out like the mathematical consequences of this, like the principle of equivalence of inertial mass and gravitational mass. But so that's like the core of general relativity, and it just started working all, it was taking this as a principle and then worked out all the equations. Mm-hmm. And then it turned out to be right. But of course they had to test it. It's like this. One example about this, for example, is a supersymmetry theory. It was within particle physics. They were, I think, most of the physicists were betting on this. So again, within the realm of particle physics, there's this the standard model of particle physics, which is like the most widely accepted theory of particles, so of electrons, protons, quarks, particles, basically. So what they're studying at CERN, they had this extension to the theory because they know that it has limits. Mm-hmm. So one of the things that is disappointing physicists nowadays is that the standard model of particle physics works perfectly. They still couldn't rule out basically any prediction of it. Now we have this, I don't know if you read about that, there was this G minus nu, the magnetic moment of the muon measurement at Fermilab, I think, in Chicago. Mm-hmm. It wasn't news, like it was hailed as one of the greatest challenges to the standard model to this day. It's something technical. I don't want to dig into that right now, just to give an idea. But again, there's this model is working so fine, and we know it's incorrect. There are some inconsistencies that need to be solved. And so they came out with this supersymmetry theory,
right? I
think during the 80s, and everyone was saying, "Oh, well, it must be this one.
This is going to be it, right? Yeah,
it's gonna be it because this theory is just so nice and it works so fine and it's like so elegant from a mathematical point of view, and there's the symmetry ideas that leads. I mean, they work so well in the standard model, so we are just extending the symmetry idea to this, again, supersymmetry. It turns out it's not working. Like in the last 10 years, they started doing these experiments at CERN. They're not finding anything of the, as far as I know, anything of the predictions that were the main predictions of this supersymmetry theory. And so people don't really know what to do with that because the theory was just so elegant, and there was this whole paper factory you know, like people just did thousands of applications on supersymmetry and working out how the world would work, how to explain and this and that within this framework.
Right. They build all these sort of mathematical castles in the sky. Right.
Yeah.
And
again, you need those castles in this case because that's what gives you predictions.
Of course.
You need to work out the consequences. Of course, given this model now, it's very sophisticated. It's not something you can do like on the back of an envelope. You need to do some sophisticated calculations and think about it thoroughly and say, okay, it's because again, if we didn't find it so far, it means it's something complicated and you need to interpret in the experiments, and there's a lot of data to be analyzed. There's a lot of it's not trivial. So you need this theory behind it, like to drive you and to push you to the limit to tell you, okay, we expect this and this and this to happen, and where this and this and this are very weird effects. Like I cannot even come with an example. I studied like 11 years ago.
No, that's cool. Don't worry about that. But you made another interesting point, which I want to highlight, which I think people don't consider often enough, is that in science, and this is one of the things that's sometimes used against certain criteria of why they might not be adequate, is sometimes we will hold on to a model even if we know it's not entirely correct, right? And this was the case with the Newtonian picture before it gave way, right? It's like, even within the world, that sort of slice of time, there were things that it did not explain or predict, right? But it did so well generally that even though people knew it wasn't entirely correct, you still held on to it, right?
Yeah.
And then eventually it did give way, right?
Yeah.
But that's just an interesting thing to think about, that we have these in the sciences, we have things that we use, that we hold on to, that we know aren't, it doesn't mean that they're totally wrong.
It's ringing a bell, but yeah.
Yeah, but they're not also entirely right either, right?
Sure. Again, it's so one thing is like the idea. That's why you call there's things that you call a theory, like a general theory or something, and then you have models. And so there's, I would say, like when you're calling something a theory, it's something that is very basic, right? It's very fundamental in a way. It's like the fundamental. There's like a high degree of truth to it. You're getting to some fundamental concepts in nature, or something that is really lays the foundation for everything else. Then models usually combine different theories, or they take some theory and make some, and they are sort of what I would call Newtonian theory right now. It's like it's an approximation to the true theory, which is general relativity theory. I mean the most likely theory of gravitation. And so in that sense, the Newtonian theory is just an approximation. So it works in many cases. It's very useful to make a lot of calculations, but you cannot really get some deep, the deep philosophical insights that you would get from that theory are wrong. About time and space, for example, about the way light travels in the universe. And so you can still use it, of course. No one is preventing you from using it, but it's not the best. It's not a real theory. I would call it, again, it's an approximation right now. You can, and we do it all the time, like in cosmology with the Newtonian approximation, to spare us some complicated calculations. In some cases you don't need to go all the way to general relativity.
Right. Right. And that opens up, I talked about this with Stephen Barr when he was on, and it'd be good to get your thoughts too. But again, there's different epistemologies that scientists and philosophers of science take, right? So sometimes when they realize what you're saying, that okay, this is useful, or this is an approximation, some people just veer towards an instrumentalist view, right? And the instrumentalists want to say that okay, whatever else this aspect of science is telling us, whether it's in physics or somewhere else, it's not real. It's just useful, right? It's a useful fiction. I'm not an instrumentalist, but this is a view that's out there,
sure.
and championed, right? So I think it's just important for people to realize that there's some very prominent people who just take that view, right? That they hold like whatever else these things are, that these theories, these constructs, they are just useful instruments, right? But they're not real. And then there are like the hardcore realists saying, well, whatever else is real, it's going to be whatever the theory of everything is, right? And that's it. And there's nothing, and there's going to be nothing more to the story. Mm-hmm.
I don't know, like in principle, there's no reason why nature should behave. I mean, in a way, like just the simple fact of making theories about nature. I don't know if it's something that, you know, nature itself should it really obey some kind of laws all the time? I mean, we're taking this for granted, but it's a sort of different question. But we're taking this for granted, right? So is it written somewhere that nature should obey the same laws, and there should be like laws and regularities at all that govern nature?
Right. Mm-hmm.
This is
and that comes from the general Christian worldview, right? The laws of nature, and a lot of people forget that the history.
Sorry, you froze.
We back?
Like a while.
Yeah, no, I just was saying, like, a lot of people just kind of forget the history of that, right? That there was this assumption, and part of the sciences, you know, they arose in the time that they did because there was a general philosophical and theological assumption that the world was orderly, stable, intelligent, right? Stuff like that. I think there's a lot of to that. But to the point about instrument, having a few technical difficulties here, friends.
I don't know what's going on.
I think it's on.
It should be all right now. Can you hear me?
Yeah. Mm-hmm. Right. But one of the arguments against the instrumentalist view is that it would just seem to be a miracle, right? That these things would be so useful if they didn't have some real truth or reality to them, right? Like it would just be an unexplainable miracle. Like why is it so useful? Like it's just a miraculous that it happens to be so useful, stuff like that. So it has to be telling us something more substantial than just being a useful fixture, right? Uh-huh.
Yeah, I think the other argument is that there are many layers of evidence, and that there are many different observations that you can do in general for a theory. And so the hard thing is like accounting for a lot of different things at the same time. So that's the hard part, because you can always sort of tailor or cut out your theory and make it, you know, account for a certain subset of phenomena. But the hard thing is finding out a theory or a framework that works for many completely different phenomena at the same time. Completely different. Mm-hmm. Because then it should really be some kind of, as you said, miracle, but whatever. It's like, unless there is some underlying regularity, unless there is some kind of general law that is really in place, then you should really explain to me why, for example, why can I, with just studying, for example, quantum physics, I can compute the abundance of elements in the universe, mm-hmm. and explain you why light is traveling from why the sky is blue, for example. Mm-hmm. Like it's the same theory that is telling you how much hydrogen is out there in the universe and how much helium is there in the universe, and at the same time you can explain to me why the sky is blue, which are right. I'm talking about two completely different things, but they stem from the same kind of theory. And so if you want to replace quantum physics, then you need to find something that is at least as powerful. You need to be able to apply it to different domains. And the same thing is with the general model of cosmology, the standard theory, because it works in very different places, in a sense. So you can explain, for example, it's not explained, but it accounts for it, at least within this unified framework, within this unified model. For example, why are there this number of galaxies? I mean, it sort of predicts it in a sense naturally. At the same time, it's telling us why the universe is expanding. At the same time, it's telling us, for example, you can also make some kind of predictions with mm-hmm. it. And one of those was the cosmic microwave background that was predicted in the 50s. It was like there were three authors that they studied this kind of Big Bang theories, and they predicted there should be then some kind of relic light coming from the initial moment, so to say. And then eventually it was found in 1967.
Right.
It was, I mean, it's not a prediction in the sense that it's something that will happen in the future. It's a theory that told us, look, we should observe this phenomenon that happened in the past, but no one has observed it yet. So it's a different kind of observation you can make.
Yeah, but it's a legitimate prediction.
It's again, prediction in the standard set. I mean, I would say in the standard terminology or whatever the meaning, it's like I predict something, it's about the future, right? It's hard to say I'm predicting something about the past, because this is technically, it's a prediction about something that happened 13 billion years ago, because what we're seeing now, it's a relic of what happened, it's a remnant of something that happened.
But we still use that type of like prediction all the time in everyday reasoning. So like, for example, if I go outside, use kind of a homespun example,
okay,
and there's water around my car, right? And now I start thinking, well, why is there water on my car? Like, did it rain? Well, maybe not, because the water is like just around my car, right? So that's kind of weird. Then I think, well, maybe my wife washed my car. And then I might think, okay, that explains the sort of restrictedness of the water on my car. But if my wife washed my car, then I bet I will find a bucket of suds somewhere around my car. And then if I go and I find that bucket of suds, you see what I'm saying? Like, that's a prediction of something that happened in the past. But the fact that I did encounter what I expect to see counts in favor of the car washing versus raining hypothesis, right?
Yeah.
So I just thought that there was something of a parallel there. Yeah.
Yeah, no, it's a good way of explaining it. That's because what cosmology is all about. You cannot really make, again, you can try to make predictions about what's going to happen in 10 years, but it's not really relevant. But you can make predictions about the distribution of galaxies within a certain environment. So should they be like distributed in a flat way? Should they be like in a filamentary way? Or should it be like isotropically distributed? There's many things that you can sort of, again, predict. And this is interesting because that's one of the ways as telescopes and observations improve, then you can try to test your theory again about everything, like by studying a single object, which would be like, I have a theory about a nation, about the whole country, and I want to study like how this general theory about the country influences a single home. So I'm watching a single home, and about this I'm trying to extrapolate what happens in the whole universe. Because the two things are related in a way. You can say that if you see a very rich home, or I don't know, you see a certain kind of car, you see some kind of like the infrastructure, I don't know, the structure of the home. It's made out of wood. It's made out of. There's many things you can infer about the climate in that country, about the GDP. Maybe you can make some kind of inference, even studying a single object.
Yeah, and that has been
and a very small one.
Yeah. And that was actually, we put that in the description of the show. Yes. So I'm glad we finally got around to that, because that's a really.
We can make a part 2 and actually talk about these kind of things, but I think it was interesting to lay like the foundation, the philosophical foundations of cosmology, because the first thing that calling the universe rare by itself, it's in a way it doesn't make any sense, because you can call something rare compared to something else, right? You have to have some baseline and say there's hundreds of thousands of universe, and we find out this lies in the tail of the distribution, but we only have one, right? How do you define rareness or uncommonness? I don't know, like for a single object.
Right, and if you subscribe to a multiverse theory, that might change how rare you think.
Sure,
things
but
are,
then
right?
You don't. You cannot. Still, you cannot say if it's rare or not, because you could say maybe it's 100,000 billion universes out there, but they all look the same.
Right, and then
How can you tell?
How do we know? Right? Yeah. No, that's a really good point. Right? It's like we don't have enough background knowledge to make that assessment.
Exactly.
Right. Yeah, this is good, because I know we were talking about, and I think this is something we'll have to do, is we'll kind of do an ongoing series where we explore I think just more more general, philosophy of science stuff is always interesting. But maybe we could dive into a little bit now of things, because we've both been personally kind of agitated at like the pop level science that's been foisted upon the public in many instances. In fact, I'll give one. We'll give one easy example here. We were both you had a nice response on Instagram to Neil deGrasse Tyson the other day, and
it was on Twitter.
Oh, it was on Twitter. Okay, yeah. And it's funny because I think we both saw it and we both said something about it independently, and then
I didn't see your answer though.
Yeah, mine was on. It was similar to yours, right? So he said in his, and this is that's so unhelpful, right? His tweet was like,
let's just quote it. Let's do things properly. I think
let's make sure we get it right. It's a tweet, so we shouldn't take too long. I would bring it up on my phone here, but I don't know where my rectangle is.
I'm looking at it just here. Yeah. Just to be, like precise, because science, something we can all agree on. We need to be as precise as possible when we define something, when we talk about something. What's
absolutely.
Where is it? Okay, yeah, sure. Here it is. So, he said, the good thing about science is that it's true, whether or not you believe in it.
Right. And I thought your response was spot on. But I essentially echoed the same thing. But why don't you go ahead and...
Okay, I read what I wrote and then you can tell me what you wrote. Mm-hmm. I said, can I disagree and say that science is not about truth, but rather about the degree of evidence-based belief we assign to certain statements? Every scientific fact has some error bars attached to it. Extremely small in some cases where de facto 99.99999% is a synonym for true. So it's a shortcut, but science, like saying something is true, it actually means I have a very high degree of confidence into this statement. But it's about the degree of belief. It's like about, this is the Bayesian. I don't know if you did something about Bayesian statistics and the Bayesian. Yeah. But go ahead, please read yours.
Yeah, no, I mean, that's exactly right. The only thing I'll add to that is these platitudes are unhelpful, and I think they keep people scientifically ignorant, right? Like there's something called the science rather than different sciences and debates about the scientific method. And okay, well, what branch of science do you want to talk about? What theory do you want to talk about? Because if we're talking about, like, my attitude towards general relativity and the science that supports that is going to be very different than my attitude towards public mass mandates and the science that supports that, right? These are wildly different categories with wildly different probability assignments, right? And something tells me when he puts out a tweet like that, he's like taking a dig at people, probably like both of us, that would say, yeah, I'm a little skeptical of the science over here in this department. And it also acts like there's this kind of like giant monolith, like just the science. Like there's just the science, which includes the scientists, and they're all saying one thing unanimously in one voice, which is obviously ridiculous, right?
It's historically false. I mean, still nowadays it's false. I mean, you can say, again, within scientific communities, there are textbook truths. In a sense, something that ends up in a textbook, then you can say it's true in a sense. It's an extremely good model of the universe, or of a cell, of an atom.
The law of sulfur, right?
It's like, this works just fine. It works like this, 99.99999%. We are sure we tested it like billions of times. Going back to philosophy, I mean, there's still the inductivist problem and induction problem.
Yeah, the problem of induction, right?
The problem of induction.
Yep.
That David Hume pointed out, and I think it's a fair point. Who's gonna tell you that tomorrow the sun is? Who's telling you that the sun will be shining tomorrow? We don't know. I mean, it's a matter of degree of belief in it, right? And so it might as well be that tomorrow the laws the laws of general relativity stop working for some reason. It's not. There's no logical contradiction to this statement. I just think it's highly unlikely. Again, I wouldn't say it's. Again, false here means it's just extremely unlikely.
Mm-hmm. Yeah, let's do an episode on Hume's problem of induction. There's a lot there's definitely a lot to be said about that and how I think it can be overcome as well. Why do you think I don't know if this is appropriate. It's getting into like armchair psychoanalysis, but why would Dr. Neil deGrasse Tyson tweet something like that? Right? How does that serve the scientific community or scientific education? Because on one hand, you hear these sort of science popularizers talk about how important science education is, right? And in fact, they never get tired of saying that. That's all they talk about is how scientifically ignorant people are. And if we only had better scientific education, we wouldn't have the mess of the world. This is constantly what's coming out of their mouths, right? But then they
massive failure.
Yeah, but then they do these things that just like feed ignorance to people about what science is, how it works, how it progresses, right? I don't know. I just want to get your thoughts on that. Mm-hmm.
So I don't know enough about Neil deGrasse Tyson because again, it's popular in Europe, but I don't really. First of all, I don't really read science popularizers, especially from astronomy, because I feel like I know enough like to go to the source directly. But I think there's a lot of. It's not serving. It's very often it's not like scientists do not have egos. Like people tend to forget this. And I include myself in this. Like sometimes when I enter discussions, then I try to refrain from that as much as possible. But sometimes you just, when you discuss some issues, like, what do you want to know? Like, I got a PhD, right? So I know and it's not to say that, having a PhD in a given field doesn't mean anything. Of course it does. And I think it's like it's a reasonable proxy for testing your for saying it's you know enough about this subject. It still doesn't prove you're right.
Right.
Like being right and having a PhD or any kind of title, they're two different things. Like logically, it's not the same. There's no, in principle, there might be no overlap at all.
Right.
With that, like there might be people with PhDs in Islamic theology. It's not that I cannot argue about Islam or reasonably, how reasonable is that religion or whatever.
Right.
Or they might be right about it just because they have this kind of, they did this kind of study. So again, that's not science in an empirical way, as there's no like evidence-based foundation as other sciences, but still it's just to say that in general, like holding a title
right
might mean something. But you always need to take it with a pinch of salt, like with a grain of salt. It's not, and this is something that scientists tend to forget to tell people because they always, when they talk to the public, they're more like they have this kind of paternalistic approach, this kind of ex cathedra. They want to talk like ex cathedra, like the Pope. They say
that's right.
This title, and this is the truth. This is like a very good example of what they do, but I could find thousands of those, like in my experience in Italy or in other countries. When you see this approach, that is very, because on the one hand, I understand that there is a lot of disappointment with a lot of anti-scientific theories going around. I don't know, like the flat earthers or this kind of bullshit that is being by and large amplified.
But give me your honest assessment, because I haven't looked into flat Earth at all. But like honestly, how many flat earthers are there really? And like, are they legitimately like a big problem in society?
No.
Because like I hear like people taking digs at them all the time.
No.
I've never met anybody who believes that ever. I haven't.
No, I think so. My take on flat earthers is I shouldn't talk. I mean, I never when they come to me and say, "Oh, what do you think about flat earthers as an astrophysicist?" To be honest, I seriously despise more people that talk about them than the flat earthers themselves, because they're giving. I think that the flat earthers in society, they have this role that they want to feel better about themselves. So there might be a bunch of them, like Nazis, for example. I mean, I know I've never met an actual Nazi. Maybe one or two. Someone was really an actual Nazi, like. But still, sometimes I feel that they need to push, like, oh, there's the Nazi danger. There are the flat earthers, and people would like to talk about this because they want to feel better. You are setting a very, very low standard. And then it's easy to feel like a better person because you say, oh, look, at least I'm one or two steps above this idiots.
Yeah,
Which
yeah, I think you're absolutely right. Right, it's just such an easy target,
exactly.
and that's why, like, look, I'm not defending flat Earth theory, but I guess in a sense, I'm defending. I guess I'm in a sense defending the flat Earthers out there, right? Because, like, first of all, I never met one, right, ever. Or if I did, I didn't know it, right? But like, I hear these things like when people will say, like you said, they'll take digs at people. Like, I'm like, and I just scratch. I'm like whatever other troubles we have in society, we have a lot. Is it really the fault of people who think that the Earth is flat? Like, is that maybe? I'm a little skeptical of that, but
Yeah.
right. It's just it's an interesting thing. Just easy targets, right?
It's a very easy target. So that's something that people like having easy targets, like pointing, I don't know, yeah, pointing the finger. There's this kind of witch hunt that is there must be some kind of some ancestral remnant or some part of the brain which is geared towards the pleasure that you have when you can find someone who's worse than you and just point your finger and judge him or her or whatever. And again, that's people like having like someone who's like looking at knowing that there is someone who's worse than you. That's the thing.
Right.
And
Yeah.
again, but I think scientists, in general, I mean, I hear unscientific theories in the sense that people make false claims about nature or universe as we know it. Again, claims which are at odds with what we know so far. Maybe I'm not excluding that your claim is might be right in 2,000 years because I don't know, because of some change in whatever. But this is clearly at odds with what we know so far. So it's a false claim. It's a very unlikely. Again, if I want to be precise, we would say it's a very very unlikely claim. So
It's a very low probability,
very
right?
low probability.
Yeah, that's helpful. What should and people can comment either now or after, but I do think it would be really fun if we dug something up every week, and that I guess parades itself as being scientific in a sense, but but it's generally unhelpful to say the least. And I think that there's no shortage of material out there that we could start with. And it's not because we want to necessarily. We can even leave names out of it. Did somebody say they like Hollow Earthers? I just watched a new Godzilla and King Kong movie,
Okay.
and the whole idea was that there's a Hollow Earth, and
Okay.
that's where the monsters come from. So yeah, that was pretty sweet.
Makes sense.
Yeah, makes total sense, right? But I don't know. Yeah, what are you thinking, Eduardo? Where should we?
Yeah. Again, I was telling you, I think what we mentioned right now, this tweet is a good starting point. In a sense that I would like to comment and discuss this kind of science. I mean, at least what is being sold to the public as science, whereas it's clearly not, or it's like at odds with the philosophy of science or the evidence,
Yeah.
because it comes out very often, and I think it would be just brainstorming around these things that pop up too often, and this kind of again when people talk ex cathedra, like authority talking, because I'm a scientist, and then my statement is true just by virtue of me saying
Right.
that. It's not by its own virtue, but which is the most unscientific thing you can say there. But anyway, like I would like to do something along these lines, and even just commenting the news or whatever. It's
Let's do it.
if we
So
get
yeah, we're gonna do two things next time. We're gonna find something that will be juicy and interesting and controversial and spicy. And I also want to talk about Hume's problem of induction, just because I think that's an
right,
interesting
yeah.
topic. So we can do a twofer there.
Okay.
If that's cool with you.
That's cool with me. Yes, I am not so familiar. I mean, I read Hume. I remember maybe 20 years ago. I was reading his Inquiry into Human Understanding, which is a book I really enjoyed back then. But it was 20 years ago. So
Right. Yeah, opinions can change over over that time.
I don't know. I mean, I think Hume had a huge influence on my philosophical thinking on many things. But
He did it for me for a while too. Now I look
oh,
back at Hume and with much disagreement on things, but
okay.
he's
But
a
that's
very
stuff,
important
right?
he's a very important figure, right? There's
Absolutely.
like he's not somebody that you can or should skip in the history of philosophy at all. So yeah, I think that would be a good thing to take up. But for my audience, Eduardo,
Yeah.
before next time, where can people keep up with you and your stream and your podcast and all that?
I got. I mean, you get the easiest way is just to tune in on my YouTube channel. So Gatto Cherry 666. There's then you can find all the links. I mean, my GattoCast podcast is online on Spotify, on Apple Podcasts. I mean, on all the major platforms. And it's mostly in English so far. I got a bunch of episodes in Italian, and some of those are in Spanish as well. But yeah, that's it
Just
so
like
far.
spelled like that.
Exactly.
I love StreamYard. It's so
Oh,
functional.
yeah.
Yeah. Well, good stuff,
Cool.
man. I guess we'll cut the stream here, but gentle listeners and watchers, please subscribe and like, and if you enjoyed it, consider ringing the bell and all that other good stuff. Any final words on your end, Eduardo?
No, thanks for the conversation. It was amazing. So again, it's always a pleasure. It's always a pleasure.
Looking forward to the next one, my friend.
Looking forward to the next